Download this code from codegive.com, link in the description below. The Moser circle problem, a detailed tutorial. The Moser circle problem, also known as the circle division problem or the cake cutting problem, is a classic combinatorial problem that asks, what is the maximum number of regions into which a circle can be divided by connecting endpoints on its circumference with straight lines? The points are assumed to be in general position, meaning no three lines intersect at a single point inside the circle. This might seem like a simple geometry problem, but it quickly reveals itself to be surprisingly deep and connected to concepts in combinatorics and polynomial functions. Let's dive in. 1. Understanding the problem statement. Setup Imagine you have a circular cake. You mark endpoints on the edge of the cake. Goal You connect every pair of these endpoints with straight lines. Think of cutting the cake with a knife. The key is that no three lines intersect inside the cake at a single point. This is the general position constraint. Question How many separate pieces, regions, will the cake be cut into at most? We want the maximum possible number of regions for a given n. 2. The trivial cases and pattern recognition. Let's start by visualizing the first few cases. N equals 0 no points, so the circle remains in one piece. Number of regions, 1. N equals 1 1 point, no lines. Number of regions, 1. N equals 2 2 points, 1 line. Number of regions, 2. N equals 3 3 points, 3 lines. Number of regions, 4. N equals 4 4 points, 6 lines. Number of regions, 8. N equals 5 5 points, 10 lines. Number of regions, 16. It seems like the answer is simply 2 sup n 1 sup, right? For n equals 0, 1, 2, 3, 4, 5, we got 1, 1, 2, 4, 8, 16. This leads to a plausible, but unfortunately incorrect, guess. 3. The disappointment, why the pattern breaks. Let's try n equals 6. If the pattern held, we'd expect 32 regions. However, if you carefully draw the diagram for n equals 6, you'll find that you get only 31 regions. This is a crucial point. The simple exponential pattern breaks down. This highlights the importance of rigorous reasoning. Visual intuition can be misleading, especially when dealing with combinatorial problems. 4. Finding the correct formula, a combinatorial approach. To derive the correct formula, we need to consider the different ways the lines divide the circle. We have to count both the number of lines and the number of internal intersection points, as each intersection point adds a region. Here's the breakdown. Number of lines each pair of the endpoints on the circle defines a line. The number of ways to choose 2 points from n is given by the binomial coefficient, c, n, 2, equals n. Slash, 2. Asterisk, n2. Equals n asterisk, n1, slash 2. These are the lines that cut across the circle. Number of intersection points each intersection point is formed by the intersection of 2 lines. Each line is defined by 2 points on the circle. Therefore, each intersection point is defined by 4 distinct points on the circle. The number of ways to choose 4 points from n is given by the binomial coefficient, c, n, 4, equals n. Slash, 4. Asterisk, n4. Equals n asterisk, n1, asterisk, n2, asterisk, and 3/24. These are the interior points where the lines cross, creating new regions. Asterisk number of intervals on each line. Asterisk each line segment that divides the circle is determined by either the intersection with another line, or by the endpoint on the circle. Each intersection point adds one interval to the two lines intersecting at that point. Since each of the C, N, 2, lines has two endpoints on the circle, plus all the intersections, the number of intervals on those lines are given by C, and 2, plus 2 asterisk C, and 4. The number of segments that divide the circle is given by this formula. Asterisk Euler's formula, modified for this problem. Think about a planar graph, a graph drawn on a plane. Euler's formula states, V, E plus F equals 1, where V is the number of vertices, E is the number of edges, and F is the number of faces, regions. We need to adapt this for our problem. Asterisk vertices, V. The vertices are the endpoints on the circle's circumference plus the intersection points inside the circle. So, V equals N plus C, N, 4. Asterisk edges, E. The edges are the line segments that divide the circle. We have C, N, 2, lines, and each line is split into several segments by the other lines. So, the number of intervals on these lines that divide the circle will be C, N, 2, plus 2 asterisk C, and 4. But we need to account for the line segments between adjacent point pairs on the circle as well. These are boundary edges which are not covered by the prior. There are n such edges. Therefore E equals C, N, 2, plus N plus 2 asterisk C, and 4. Asterisk faces, F. The faces are the regions we're trying to count. Let's call this R, for regions. Now, we can solve for F, R, in the modified Euler's formula. In our case, the outside of the circle is not counted. So, let's use V, E plus F equals 1. V equals N plus C, N, 4, and E equals C, N, 2, plus N plus 2 asterisk C, and 4, and F equals R. So, the equation looks like this. N plus C, N, 4, C, N, 2, plus N plus 2 asterisk C, and 4, plus R equals 1. Simplifying, you get N plus C, N, 4, C, N, 2, N, 2 asterisk C, and 4, plus R equals 1. C, N, 4, C, N, 2, plus R equals 1. R equals 1 plus C, N, 2, plus C, N, 4. Substituting the binomial coefficients, we get the final formula for the maximum number of regions. R equals 1 plus N, and 1, slash 2 plus N, and 1, and 2, and 3, slash 24. 5. The final formula. The maximum number of regions are into which a circle can be divided by connecting endpoints on its circumference with straight lines, no three lines intersecting at a single point, is 6. Code implementation, Python. Here's a Python function to calculate the number of regions for a given n. Explanation of the code asterisk. 1 binomial underscore coefficient, n, k, asterisk. This function efficiently calculates the binomial coefficient c, n, k. It includes optimization techniques to avoid large intermediate results and unnecessary computations, using symmetry. This function is optional and only needed if you uncomment the binomial underscore coefficient based code. 2 Moser underscore circle, n, asterisk. This function calculates the maximum number of regions for a given n using the derived formula. It's best to use the direct formula-based implementation for efficiency. 3 example usage *. The for loop demonstrates how to use the function for different values of n. 7. Key takeaways and general principles. Pattern recognition can be misleading. Always be careful about relying solely on observed patterns. Rigorous mathematical proof is crucial. Combinatorial reasoning. Many geometric problems can be solved using combinatorial arguments, by carefully counting the different ways objects can be arranged or selected. Euler's formula. Euler's formula is a powerful tool for relating the number of vertices, edges, and faces in planar graphs. Understanding how to adapt it to specific problems is valuable. Problem decomposition. Break down complex problems into simpler, more manageable parts. In this case, counting the lines and intersection points separately. General position assumption. The general position assumption, no 3 lines intersecting at a point inside the circle, is critical. If you remove this constraint, the number of regions can change significantly. 8. Variations and extensions. Higher dimensions. The problem can be extended to higher dimensions. For example, what is the maximum number of regions a sphere can be divided into by planes? Removing the general position assumption. What happens if 3 or more lines are allowed to intersect at a single point? The problem becomes more complex, as you need to account for the multiplicity of the intersections. Other shapes. You could explore similar problems with different shapes, such as a square or a rectangle. The Moser circle problem is a fascinating example of how a seemingly simple geometric question can lead to deep mathematical insights. Understanding the solution provides valuable experience in combinatorial reasoning, problem-solving techniques, and the importance of rigorous proof. It's also a reminder that our intuition can sometimes lead us astray.